Hi everyone, this is Siddiq. I'm going to present our paper on privacy enhanced speech emotion communication using deep learning aided edge computing. The outline of my presentation consists of motivating the problem, proposed solution, evaluations and results, conclusions and future work. Motivating the problem. If we see a typical speech emotion recognition system, it consists of emotional speech or features that are given to deep learning model for emotion classification and prediction. And due to the recent advancements of deep learning models, the performance of SCR system is increasing day by day. However, if we see in this system, it contains emotional speech or features that can also have sensitive information that can be used by an adversary for speaker, language, gender identification. We highlighted some problems in state-of-the-art system. If we see a state-of-the-art emotion communication system, it has three components. There is the end devices speech sensing layer, where they collect the raw speech and transmit to edge nodes that just act as a relay and hand over this information to the network for remote cloud, where they perform emotion analysis and make some decisions. And here we see the raw speech is transmitted to the network that is highly vulnerable to the adversarial attacks. And in this work, we want to hide the sensitive informations and transmit some private features that can enhance the robustness of the system. So this is our proposed solution. We have the same speech sensing layer where we record the speech, and then we compute the speech feature at the edge node at the end devices and transmit this feature to the edge clouds, where we deploy a privacy preserving model that extract the privacy preserved feature, and then this feature we transmit to the remote cloud for emotion classification and decision making. In this way, we can hide the sensitive information in the speech features as much as possible before transmitting to the remote cloud. How we compute the privacy in preserving features? So we deploy a deep learning model at the edge. It consists of an encoder which use the emotional features and encode into the compressed form, and the decoder use that features to reconstruct the input features as much as possible. And then we also connect three classifiers: speaker classifier, gender classifier, and language classifier, that use the compressed feature and try to classify the speaker, gender, and language. And then we use the gradient reversal layer that multiply that back propagate the negative of these weights to the encoder. In this way, the encoder try to update the compressed feature by removing the information about the speaker, gender, and language identification. And these compressed feature we transmitted to the remote cloud for emotion classification or decision making. Evaluation and results. We use different data set. First one is EmoCap. We use 4 emotions: angry, happy, neutral, and sad. And then EmoDB, we use 7 emotions. Next one is Emovo. We use same 7 emotions. And for BiomoDB, we use 4 emotions. And if you see, all these datasets have different number of emotion, and their labeling is also different. To make it similar labeling, we map this information to binary valence, where the negative valence consists of angry and negative emotion, and the positive valence consists of positive emotions. So we map these all data sets which have English language, German language, Turkish language, and Italian language, and these are the mapping. So we classify these emotions using a classifier in negative valence and positive valence. Evaluation and protocols. So we, for the input feature to the model, we use the compare feature for input representations, and for the deep learning model, we use the feed forward neural network that consists of encoder and decoder with 2 hidden layers of hidden units, 2000 and 1000 each, and we set the dimension of latent features, that is the compressed features, 512. For classification, we follow the leave one speaker out scheme and train the support vector machine to on the privacy enhanced feature to classify the emotion. We select the radial based function kernel and perform the grid search using the validation data to pick the optimal parameters of support vector machines. We assume here the attacker, that is the adversary, has access to the testing data or portion of test data where he knows some labels about the language, speaker, and gender labels. And then for speaker, we use a user identification where the attacker wants to know the person is a member of the system or belong to the training set. So here are some results. We compare the result on the standard feature using different methods. Here, if we see the features, compare feature, the features by autoencoder and the PCA on emotion classification, they achieve 71.5%, 69.5%, and 66.5%. Along with the emotion classification, when we use these features for gender, user, and language identification, they achieve highly good accuracy. For example, if we see the compare feature here, they are achieving above 90% on gender identification. It means if we transmit the emotional feature on the network, it also contains the gender information, user information, language information with highly accurate, that can be used by an adversary to identify these with highly accurate results. But in contrast, on the privacy preserving feature using our model, we are achieving 68.7%, that is comparable with the previous methods. But if we see here, we are minimizing the performance on gender, user, and language identification. So this shows that our proposed model can enhance the robustness on a network for speech emotion recognition system. We also evaluate the model using different dimension of privacy enhanced features. So here are the results. We use 1024, 512, 200 65 and 128. We can see that by using the small dimension of the feature, we are achieving slightly less accuracy for emotion, gender and language identification. However, we can minimize the bandwidth usage of the network using the small number of dimensions. So this shows like our proposed model also gives us opportunity to use the small number of features to minimize the bandwidth usage. Conclusions and future works. So we propose a novel deep learning based privacy enhanced representation learning architecture for emotion sensing application that can be used over in the network to perform emotion classification. So the proposed network leverages edge nodes to encode speech features to the robust and compressed representations that can be transmitted to the remote network. We use adversarial learning framework for privacy preserving feature by unlearning the information about the speaker, gender and language identification. Based on the result, we show that the proposed model enhanced the privacy of emotion sensing system in terms of speaker, gender and language without significantly degrading the emotion identification performance. In our future work, we aim to study the gains of deep learning based emotion communication system under the real edge based mobile clouds and cloudlets scenarios. Thanks for watching.